Hi everyone, and I'm happy that AI seminars are fully in person. I missed days in like the COVID days when it was remote. Today I'm going to discuss a project I've been working on for a while, which is about paraphrase generation and its effect on a text classification task and basically its impact on prompt optimization or parameter efficient tuning methods that is popular in NLP these days.
Sorry, Saeed. I
Yes.
think you really need to project while you're.
Use your outdoor voice.
Oh, okay.
Yeah.
Yeah, I will speak louder.
Good, thank you.
Thank
So
you.
for the presentation, I have basically two main sections. So in the background, I'll talk about my general, idea and PhD about generating like latent text and how it can be applied to different tasks, including paraphrase generation. And then first, I will show you the results about the impact of paraphrases, how they are improving the performance for language model few-shot fine-tuning. And then later, I'll talk about the actual objective that we can use to, train a paraphrase generator. And then briefly, we'll mention what is my future direction in this area. So, my main goal is to focus on conditional text generation problems because a lot of tasks in NLP are being modeled as a CTG or conditional text generation problem. For example, in question answering, the input X is a context, a paragraph, a document, along with a question, and then the language model is supposed to generate an answer for your question. Or in machine translation, you can say X is the, an English sentence, and then Y is a French translation. So a lot of tasks in NLP are currently modeled as a conditional text generation problem. And the research in deep learning architectures for NLP have well-developed models for this like learning this distribution. So anything for learning sequence-to-sequence models or encoder-decoder models based on transformers are well designed to learn a conditional distribution of Y given an input X.
You need to really keep it on top of mind to speak loudly. I don't know if we can get it through the HDMI in the room. I could take 1 second to see if I can get it to do it.
There's a way to change the settings.
Okay,
Try it. See how that is. I'm not sure if we're plugged in actually to that.
You could go, yeah, for the.
Okay, speaker.
Mhm.
Let's try this.
Okay, can
Okay.
you talk again?
Is it better now?
Is that better?
Yeah.
Okay, good, okay. Thanks, Bobby.
I'll try to speak louder. So I was mentioning that the recent sequence-to-sequence models are well designed to learn this conditional text generation problem. Also, that the recent language models, such as like GPT series, Llama series from Meta, and Gemini from Google, they are only the decoder models, which basically is the right block of the transformer architecture. They're by proper prefixing over the input X and only training over the output Y, they're using a decoder only language model for learning these conditional text generation problems. Now, it's not just the question answering or machine translation tasks, even text classification are being modeled as a conditional text generation. So here I have a sentiment classification example. So the input example is I love free pizza. And we want to classify it into two classes, positive versus negative. The way we do this with language models currently is by adding the text in red, which is the prompt or the query. And then we ask the language model to complete the text. So the language model is supposed to generate, for example, this experience was great. And if the probability for generating great is higher than the probability for generating bad, terrible, or disgusting, then we can say that this is a positive class. And the text that you see here in blue is something, it is called instruction or task description that people found out that if they prepend to the input can help the language model to perform better for, uh, these tasks. So as you see, this is an example of a text classification being modeled as a conditional text generation problem. Now, about my idea and what I study so far, or what I plan to study in the rest of my PhD program, is this concept of generating latent text for improving the CTG problem. So our CTG problem wants to map X to Y. And my idea is that let's first generate Z, which is any latent text or sequence of text. And then we should learn to generate Y given X and this extra sequence Z. So to motivate this, this is another motivation that I will talk in the future direction, but you can think about question answering where X is a document or a paragraph or even an image if you're thinking about like visual question answering systems. And you're asking a question, for example, this one here, like which one is better, cupcake or protein bar? So to answer this question properly, the idea is that maybe we should generate some sub questions or these latent sequences Z. And these sub questions could be something like asking for the nutritional facts of a cupcake, nutritional facts of a protein bar, or how much sugar is healthy per day, how much protein is required for adults per day. And once we answer these sub questions, then we can properly or factually form the final answer and generate Y. So this is the kind of my goal, like learning latent text for improving a CTG problem. And as another application of this problem, here we'll talk about like in the rest of my slides, I'll talk about paraphrase generation for text classification, where the X is a sentence or a paragraph, Y is a class label, and the Z, this latent sequence could be or is a paraphrase of X. And by paraphrase, I mean any text sequence that retains the semantic meaning of X, while it syntactically and lexically is different. So to provide an example here, this is from one of my data sets. It's called AG News dataset, where you classify paragraphs. So these are news headlines. And the labels that you have 4 classes. Your paragraph is about world, sports, business, or tech. Here's a sentence about a sports event. So it says that a US heavyweight, Roland Gardner, lost his Olympic title Wednesday after being beaten in a semifinal stage of a Greco-Roman wrestling event by someone from Kazakhstan. So the paraphrase that here is in green. You see that it conveys the same information. It doesn't remove any information from the X. It doesn't add any extra information like something that is not an X, but its structure is different than X. So here we see it starts from the time phrase on Wednesday, and then there's a little bit change in how we frame it in terms of the grammar and the structure of the sentence. So, and as an extra motivation for why I'm trying to do paraphrasing, we have some prior research that says that it's important, even when we communicate with humans, it is important how we frame a question. So if you want to know, there's research showing that if you want to know how much a child knows about the topic, it's important to focus on the wordings of the question that you're asking from a child. Or even adults are influenced by different wordings of a question. For example, in opinion polling, if you may frame your question differently, you may get different results. So the research question that now I'm studying here is, should we rephrase an input text when we want to query or make predictions with a language model? And if we do so, if we consider these paraphrases, will the prompt optimization techniques that we have are like, will the performance of the prompt optimization techniques that we have will be better with paraphrasing. So to formalize this idea, it's so simple. So we're dealing with a text classification task where we have training examples for like we do stochastic gradient descent. So we have a mini batch of training examples, X, Y, Y, I, and the main training objective is just the data log likelihood. We're optimizing a parameter set data for the language model, and now the idea is if we have a perfect paraphrase generator, we could generate M paraphrases. Here I call them Zij for the input Xi. J is the subscript enumerating over the paraphrases. And then we can now update our data log likelihood by considering the loss or the object or the performance over the paraphrases. So basically by paraphrase generation, it's like we're creating some synthetic data set where we use the same label yi for that xi. And even in the inference or the testing phase, we can consider paraphrases, like we can do some sort of ensemble inference by predicting the best y, where the y basically maximizes the this augmented objective. So it's not just the best y for the input, but also the best y for other paraphrases. So that was the background and the motivation for paraphrase generation. So if there's any, like if there are any questions so far, I can answer.
I think we're okay.
Okay. So in this section, I'm not gonna assume that we have a model that generates paraphrases, and I will talk more about the effect of these paraphrases for downstream language model tuning. So I'm going to study the effect of paraphrase generation on multiple language modeling techniques. Here I've listed the abbreviations, and the experiments that I've done are across like 6 classification tasks. And I'll briefly go over each of these techniques. So the simple ones that I can mention here is the no tuning approach, where it's a zero shot, training, basically no training, but still we include those prompts and instructions for the classification task. And then we also have all tune, where we update all the parameters of our language model. And in this case, the language model is a Roberta large language model. So it's it's an encoder-only language model trained with masked language modeling objective that will predict the replacement of a mask token. And it's not a large language model. Roberta Large has like around 355 million parameters, so it would be considered as a medium-sized language model. As one of the techniques you may be familiar with is called in-context learning, or what some people might call demonstration learning. The idea is that if we have the task instruction, the original input, and the prompt, let's also augment the the context, the input context, with some training examples where we actually demonstrate what would be the output for some of the sentences. So those sentences are usually picked from the training examples. But by doing this, it's been shown that the performance of the downstream language model can be improved. So this is the ICL, or in context learning technique. And especially with larger language models, this technique starts to work really well. But with the smaller language models that I will show in the experiments, the other techniques are better. So in context learning is not the perfect approach. When we think about the classification tasks, like one idea is that language model eventually generates some hidden vectors in the final layer of its architecture. So maybe we can do some sort of average pooling over these feature vectors, and that can give us a feature vector for the sentence or a feature vector for the paragraph. And then we can build a classifier in this case, I've tested with a 2-layer nonlinear feed-forward classifier over the encoder's last layer hidden representations. And the only part that we're optimizing is the classifier itself. Language model is fixed because it has been pre-trained on a lot of text. We don't want to change it. We just use it as a feature extractor. And yeah, depending on how many dimensions you want to include in the classifier, which is a neural network, so you're introducing this many parameters. 1048 is the number of dimensionality in Roberta large model. So I'm describing the techniques that I've included in my study. One of them is called the discrete prompt optimization technique. Originally, it's called the auto prompt. With my abbreviation, I call it GS technique, gradient search technique. The idea is that we want to search for an alternative instruction. So here is my initial instruction in blue, which says classify this sentence as great if the sentiment is positive, terrible if the sentiment is negative. So the gradient search starts by considering one token in this instruction and trying to find another token from the vocabulary that will increase the label log likelihood. So this technique is a search-based technique. You don't need an optimizer like Adam. You don't update any parameters in the language model. It's a search-based technique. And your search, basically, the main part is this equation here in the middle where you want to find top k candidate tokens to replace a particular token pi in your initial instruction. And you basically dot product the embeddings for the token pi with the you dot product the embeddings of the token t with the gradient of the label log likelihood with respect to the embedding of your alt token pi. So you basically approximate the change in the label log likelihood if you had replaced token pi with another token t. And by considering top k tokens, now you have candidate set of tokens, and for each of those you can generate a new prompt. You can see how those prompts are performing on another mini batch of data, and you basically keep the best prompt. So it's a search-based technique. In different iterations, you do the search, you do 1 and 2, and you find a better prompt. So this is an example of a discrete prompt optimization techniques, and it shows it improves performance of the downstream language model for text classification, but obviously it's not the perfect approach. The next technique is soft prompt tuning, where the idea is that instead of searching in the discrete space, we know that these discrete tokens eventually will be converted into feature vectors inside the transformer architecture. So let's just consider there is like a 2D matrix we call prompt embedding matrix that is trainable, and let's just train these prompt embeddings in the language model. So the idea is simply just by concatenating a 2D matrix along the feature vectors computed for the input tokens. And if you want to optimize the language model, you only update the prompt embedding part. Although the research shows that if you have enough training data points, soft prompt tuning can be really good. But in my experiments, which are in few shot learning, this technique is not the best technique, and I'll describe it in the results. Then there's also, we've included other, efficient tuning techniques. One is just update the language modeling head. And this is again, the mapping that you do from the hidden state to each token in the vocabulary. And the Roberta large model uses around like 50,000 tokens in the vocabulary. So the number of parameters that you have to update with this technique is way more than the soft prompt tuning technique. Similarly, you can do in-tune technique where you're updating the input embedding of a language model. So it has the same size as the language modeling head. It's just it basically tries to extend soft prompt tuning and update every embedding vector that the language model has in the embedding table. But it may not be perfect because you're now changing everything the language model has learned from a pre-training stage. And then eventually the last technique, which is the LoRa technique. I know there was a AI seminar a couple of weeks ago about the LoRa and how to optimize LoRa. So when I started this project, I focused on just LoRa as an example of such techniques. So in LoRa, we don't update the pre-trained weights. Actually, we try to learn an adaptation through down projecting into a lower rank and then up projecting to the higher rank. And then we only learn this orange parts. Okay, so I described the techniques. Now my experiment setup is a few shot fine-tuning setup where I randomly create train validation splits. They have equal sizes, but I only have 16 training examples per class label. So if it's a binary classification, I only have 32 examples. So we don't have a lot of training examples. And then we average results across, these five created train and validation splits. About the input format here, I'm emphasizing that I'm using instructions for datasets given by one of the prior works in these datasets, and also the red part, which is the query or the prompt, and I'm using a Roberta large model, which will predict the token in place of this mass token. Now, the first experiment is about why do we need fine tuning? So here is on the y-axis, we have different LM tuning techniques. Blue is the no tuning, red is the in context learning, CLS is this yellow one, then we have gradient search and then soft prompt tuning. And we have the average accuracy across these 6 data sets that are further averaged across 5 train validation splits. And as you see, in context learning is improving over no tuning, but eventually discrete prompt optimization and soft prompt tuning are better. And classifier fine tuning, unfortunately, is not a good approach. Now, about the main hypothesis that we had, which was about what if we augment the training mini batches with paraphrases, we see consistently improved results across kind of all of these techniques, especially a very significant improvement for soft prompt tuning, gradient search, the other techniques which are not popular these days. We also see improvements with recent techniques such as LoRa or even all parameter fine tuning, and which basically verifies our initial assumption that paraphrase augmentation is really important, and all these prompt optimization techniques can benefit from paraphrase augmentation. So basically, we want to train few parameters in the language model, and to get the best performance, maybe one idea could be to do paraphrase augmentation. I specifically want to mention that the LoRa's performance on 4 of the data sets, it outperforms slightly over the case where we don't use paraphrases, but on 2 of the data sets, we see some sort of a negative result. Although that if we could extend the experiments on more data sets, it would be a better experiment. And as the last slide for the section, I want to emphasize that we're augmenting paraphrases over, in the training phase. And one might think that this is helping with the robustness of the text classifier against these paraphrases. which means that if I generate a paraphrase of the input, the prediction shouldn't change. So here in the x-axis, I have inputs at different rankings. The input as rank 0 is the original input given by the test example. And the inputs at rank 1 until rank 8, these are paraphrases being generated as different rankings. So the top paraphrase is at rank 1. And as you see here, it's a little, yeah, it's not fully visible here, but in the case where we don't include paraphrase augmentation in soft prompt tuning, we see that the performances are going down if we are using a paraphrase of the input test. And by paraphrase augmentation during training, although the performance goes up, for example, for the paraphrase being generated at the rank 3, we see that its performance is higher than even the original input for the case where we don't use paraphrase augmentation, but still the performances are dropping for paraphrase at different rankings. So this shows that still text classifiers are not fully robust to different paraphrases. So part of this decline is because the paraphrase may not be optimal, but also there are cases the paraphrases are optimal, but the text classifier is not performing really well. So it's not robust to paraphrases. Okay, so that was the end of the first section, which was about the effect of paraphrases for text classification. If there are any questions so far, I will be happy to answer.
Quick question, some very impressive results. You didn't have any error bars. Is that significant difference? Or is that a statistical test or is that just, it looks bigger?
I haven't done statistical significance, but by considering the standard deviations, yes, they are consistently better. So I do have standard deviations, and we've included in the main basically paper that shows the results. But here I just plot the differences just to visually see the difference, but they are better.
Even things like lower the bottom line, that's also statistically significant better, or
Which one? The
bottom line?
Laura.
So these ones are I'm sure it is statistically significant on 4 data sets. But when we show the average results here in this plot, it may not be, but it is significant across 4 data sets.
Thank you.
I have a question about what is the ensemble inference? How is it done, the algorithm?
Yeah, so the ensemble inference was basically if you're predicting the label y for a test example, it should not be the best label for the input xi, it should be the best label for the input xi and also for the paraphrases.
Okay.
So it's not doing voting, it's actually adding the probabilities.
Okay. Okay, if there are no questions, I'll go to the second part.
You have a question for the line graph, the very last slide.
Okay.
So here the dash lines don't have paraphrases at train time.
Yes, no paraphrase at one time.
The 8 test examples, the 8 test paraphrases.
Yeah, test paraphrases.
One other question, if you were to ask me as a native English speaker, would I agree with the ranking? Is it really obvious how much worse the second, third, fourth ones are than the first one?
Russ is asking what's the quality of the paraphrases as you go down the rank?
Could you give us an example just so we can see, yeah, that's crappy, that's crazy.
I will show you an example and we'll discuss how the quality of these paraphrases. On one of the data sets, I will show an example that the paraphrase is grammatically correct. They may include some wrong information or some sort of hallucination, but they're grammatically correct.
Okay,
I actually have one more question, which is, it seems like there's kind of two components here. There's the training with the paraphrase, and then there's the inference with the paraphrase. And I'm kind of wondering if you have one but not the other, do you see improvement, or do you need both?
Yeah,
or-
I originally in my slides, I did have here. So it was another basically plots here that it consistently improves. So actually, let me do it really fast here. So so basically what we need is yes, this part didn't work out.
So it's usually between them.
Yeah, it's in the between.
That's-
Next something, yes. Just few seconds.
this is all in paper.
I think this is on archive. Saeed, I understand the like want to get the graph, but I think we need
Yes,
to go.
okay. Going back to my presentation. Okay. Now the second part is about how do we generate these paraphrases? So practically speaking, if you have an application that you want to augment the data, you could use one of the like this large language models, GPT-4. Back then when I started this project, there was no GPT-4, but ChatGPT, GPT-4, you could generate paraphrases from these methods. But you should know that if they make a mistake, like if the paraphrase changes the class for your classifier, then you cannot fix the paraphrase generator to basically update itself to generate a different paraphrase. And also because we wanted to study some training objectives for fine-tuning a paraphrase model, we started by training a smaller T5 based model, which is an encoder-decoder transformer on outputs of the ChatGPT, where we asked ChatGPT to generate 5 paraphrases for each input for some of the data sets, and then we basically teach or train the T5 based model to generate these paraphrases. But what we also want to study is that we also want to fine-tune this paraphrase generator on the classification dataset, because we want to make sure that the paraphrase generator doesn't generate a paraphrase that changes the class if we use that paraphrase for text classification in the downstream text classifier. So to model and to define an objective for the paraphraser, we basically try to marginalize a joint distribution that we have over the class labels and the paraphrase Z, given the input X. We want to marginalize every potential paraphrase, and then we basically optimize the data likelihood that we have from the training examples. And we factorize the joint distribution into 2 parts, where the first part is responsible for generating the paraphrase, and the second part, which is the classifier that predicts the label for that paraphrase. So you see here, there are like 2 models now parameterized differently. And actually training both at the same time is challenging. So what I do is we have a pre-trained language model. We're going to use it that is fixed. We're going to use it to give feedback to the paraphrase generator. And once we fine tune the paraphrase model, we'll generate those paraphrases and augment the training mini batches. So the results that I showed earlier in the previous section was basically after fine-tuning this paraphraser. Now, there are kind of 4 learning aspects that I've been studying for this problem, which I will describe them in detail. So the first aspect is how we want to approximate the gradient. So here you see we have a marginalization over the space of all paraphrases, so it is intractable. So how are we approximating the gradient with respect to the theta par? And also I'll describe that. So one of the techniques is basically policy gradient, and then in terms of rewards, is there any benefit of using normalized rewards versus basic rewards? And then I'll describe 3 text decoding techniques about how we sample paraphrases Z, and also 2 techniques that we want to enforce some sort of grammatical generation in the model. So now let's talk about the gradient approximations. So to simplify the notation, I define reward for a paraphrase as the log probability of the downstream language model given for that paraphrase. And one technique to approximate the gradient is MML, or marginal maximum likelihood, where you just take samples from the paraphrase model, M samples, and you just do numerical summation. The log is outside the expectation, and if you try to write down the gradient, it will have this form where you have the gradient vector of the log of the paraphraser, where each paraphrase Zj has a weight. So here I call it a coefficient given for a paraphrase Zj. And if you want to do policy gradient estimation, that's what happens is that you're trying to push log inside the expectation. So this objective will be a lower bound of your main objective. And in that case, you're optimizing the expected reward you're getting for each paraphrase. So in this case, if you write down the gradient vector with respect to the paraphraser, it has a similar form to the MML. The only difference is the weight that you give for each paraphrase sample. And here at the down, you see that these sample weights. It seemed, MML is like a self-normalized policy gradient. It's like you're also normalizing the weight for each sample based on the actual samples that you've taken. So these are 2 different gradient estimations that we're studying. And through the experiments, I'm trying to show that MML is way robust and better than the policy gradient. Now, about the reward normalization, the idea is that rewards can have varying magnitudes for different training examples, because different training examples are not equally challenging for the downstream text classifier. And we basically can normalize the rewards among the paraphrases of a given input. So this is a reward normalization among the M paraphrases that we've generated for input. So we can plug this normalized reward in each of these gradient approximations. The next aspect is now, how do you want to sample? Because this idea is all about sampling paraphrases and learning from these samples. How do we sample? And we cannot just act greedily, because we also want to explore a little bit to find a better paraphraser that ends up in a better performance in the downstream classifier. But also we don't want to randomly search the text space, because if we generate a random sample and we try to optimize the paraphraser with that completely ungrammatical sample, actually we would lose the the grammatical paraphrases that we were generating at the beginning. So the techniques that I'm considering, one is top piece sampling, which is widely used in NLP. The idea is that you first find the minimum set of tokens in your vocabulary that has, like, for example, 95% of the probability mass, and then you just sample among those. So you reweight the probability mass among those tokens, and then you just sample from those. So, and you ignore all the other tokens that are not, you know, in the 95% of the probability mass. Also, there is a diverse beam search technique that tries to generate diverse paraphrases. So it's a modification to the beam search algorithm, and it forces a penalty if the generated text or partially generated text in different beam groups are the same. And then eventually, I'm trying to mix these two decoding techniques by collecting half of the samples from top B sampling and half from the diverse beam search, and use that mixed decoding technique. I'll show you that the mixed decoding technique actually is better than each of these methods. During inference, we always use diverse beam search, so we want to be more greedy. Now, about the last aspect of the learning problem for the paraphraser, the objectives that I showed you are basically on policy learning, where we're sampling paraphrases from the paraphraser, and then we update the paraphraser with the same samples. So this can be a problem, and I'll show you a figure that with policy gradient, it will start to generate ungrammatical samples. And then we consider two other techniques to fix this issue. One is of policy sampling, where we're going to sample from a fixed paraphraser, like our pre-trained paraphraser model, and then we're going to update the paraphraser. So in that case, the coefficients that we give for each sample will include this important ratio SZJ. The second solution is put a KL penalty if the samples that we're generating from theta par deviate a lot from the initial model. So the first term here is our main objective, and the second term is basically a KL penalty that we provide on the objective. If you have any questions, I'll now go towards the comparison of these techniques.
I think we're good.
Okay, so let me start with this slide. So here we have on the y-axis the mean accuracy over SSD2 validation splits, and here is the training steps. Each dot here is a validation, the performance on the validation data, averaged across 5 random splits. So you see that policy gradient, that green policy gradient PG with on policy learning and mixed decoding, a little bit after training, it will start to diverge, and it converges into the 50% accuracy, which is the random guessing, which means the downstream language model just receives a ungrammatical text and it just randomly guesses positive versus negative. So that's why the performance becomes 50%. If we do reward normalization, so I specify those with the suffix Z here, is this red learning curve. We see that it will start to learn, but then eventually it will start to diverge again. And the off-policy learning doesn't help much, so its performance is not good compared to the on-policy learning with the policy gradient. But the learning curves here, the black crosses, are corresponding to the MML and with KL penalization, with the KL penalty, and it is consistently starting to learn, and it doesn't diverge. And basically that's is the objective that eventually I use to fine-tune the paraphraser. So it is basically that the combination that works the best is basically MML approximation using KL penalized penalty, the mixed decoding. So I'll show you in the from the previous slide that the mixed decoding is better, and also the reward normalization. So, was there any question?
Why not just use early stopping here and take your PGZ on policy mixed that performs best?
So, this is just one example in SST2, and I'm not sure. So we do early stopping, obviously, yeah, the PGZ is better, but I'm not sure if this technique will now generalize to other data sets. So basically, I'm studying more like which objective is more robust that can be now generally applied to other 5 other data sets. Based on this performance that I see from policy gradient, I don't see this as a really robust training objective. So I hope that answers your question.
Yeah. Yeah, continue.
Okay. And so yeah, from the previous slides here, we have basically results for each technique across each text decoding. The mixed decoding is better compared to using top P only or diverse beam search only. And also the no tuning performance is around like 75%. By just paraphrase fine tuning, we get up to like 71 on average. No, 70.6. Now the last 2 slides are about now not just think about accuracy performance, think about the quality of paraphrases. So here we try to define some metrics for these paraphrases. So we have 5 metrics defined for the quality of the generated paraphrases, and then we want to report the performance of these these metrics on average across 3 datasets. Ideally, we want to know if the paraphrases are grammatical, so we check perplexity by another language model. The lower is better. We also want to check lexical diversity, which means how n-grams or unigrams and bigrams are different between a paraphrase and the original input X. We also want to compute pairwise lexical diversity between 2 paraphrases. So having diverse paraphrases, one would prefer basically that setup that you have diverse paraphrases. There's semantic similarity where we want to semantically check if Z is close to X, and also factuality consistency is based on another model that detects hallucination between 2 pairs of text. We want to know if paraphrase can contain any hallucination compared to X. So basically what we showed here is that compared to the model that is distilled from ChatGPT, by fine-tuning it on the classification data set using the objectives like MML objectives that I talked about, you generate low perplexity paraphrases. So in the last row, fin para is the fine-tuned version of the distilled T5. And we see that the perplexity is acceptable. The diversity, lexical diversity decreases, but the semantic similarity increases, and even the factuality increases a little bit. Again, this is averaged across 3 data sets, like averaged across almost 11,000 test examples. And by showing some examples, we actually looked at some of the examples here, showing that the distilled model from ChatGPT can generate hallucinations, and by fine-tuning the paraphraser, we're trying to remove this hallucination. So in this case, back to our original example, which was about wrestling event, So here is the paraphrase being generated by the pre-trained model. So the parts in green are okay, but then the language model starts to generate a part about hallucination, like a part about an extra information about the event, which says this person, Gardner, lost the title to someone, which is actually his wrong name. So this is a factually incorrect. And then it includes more extra information that is not present in the input. So losing 1-1 versus 6-1, which is not the case in the input X. So this is actually an example of a paraphrase being generated by these models. And after fine tuning, we kind of generate the example that I showed you earlier that was perfect. And we reduce hallucination with the language model. So this slide concludes the this section. So the first part was about paraphrase augmentation, the experiments showing that it improves prompt optimization techniques. Then the second part, I provide some insights about training objectives for fine-tuning a paraphrase generator, where strongly I believe that the simple policy gradient will not work. Even reward normalization is not helping, or KL penalties would not be helpful. Eventually it will diverge. MML is better. And then also I showed through some analysis that this kind of paraphrase fine-tuning will help us to have less hallucination compared to a ChatGPT distilled model. So going back to my question answering example, and this whole idea of latent text generation for CTG problems, I do believe a lot of applications, that there are a lot of applications in NLP that can be modeled through this learning framework. For example, in the case of a question decomposition, I mentioned that we're generating a sequence of latent questions, and then we're generating a sequence of answers for those intermediate questions, and then we're forming and like we're generating the final answer for our problem. So here C is the context question. We generate sub questions, then the answer for these sub questions, and then finally the final answer. So this is something that I'm working on, reading on. And a lot of learning techniques like MML versus any like policy optimization technique will definitely be a good candidate to train such systems with like these latent variables. And that's the end. I'll be happy to answer your questions.
Hi, thanks for the presentation. I have a question. So you have a classifier and also a paraphrase generator. Do you train them together, or the classifier is fixed during the paraphrase training?
Yeah, I don't train them simultaneously. So the assumption is that we have a Roberta large model which is pre-trained, so that is fixed. We fine-tune paraphraser, then we go on and train the downstream language model. So it's not a simultaneous training of these two. But I do believe that if you wanna generally think about this problem of simultaneously training these two disjoint parameter sets, one idea could be simultaneously training both, but it could be less stable.
Also, regarding your last point about reducing hallucination of the
Okay.
paraphrase. So a few questions. First, you observe the hallucination. Is it obtained from the GPT models, or is somehow hallucinated by the fine tuning? So the red part, the hallucinated part, is it just where did it come from? Come from the
This is from not directly ChatGPT API. It's from the model that we pre-train on ChatGPT outputs. because the model from ChatGPT API, so one reason that we don't use ChatGPT API as a baseline here is because it is not like reproducible. So in 6 months it will change. So here, this is a model pre-trained on ChatGPT output. So we get outputs from ChatGPT for around like, yeah, 500,000 sentences and their paraphrases. Then this is the model trained on that data on the outputs of ChatGPT, and then that model can hallucinate. But by doing this fine-tuning, we reduce that hallucination.
Okay, finally, it's like maybe the ChatGPT already hallucinate in the data itself is hallucination. That's why the model trained on data sets also contains hallucination, but it's also possible that model then tend to hallucinate. So do you have like result on this fine-tuned paraphrase? Like, would that be a hallucination be better or no? I mean, demos will can generate grammatical incorrect sentences because you fine-tuned to use a classifier. Anyway,
Sorry, are you referring to if I have checked that I have less hallucination in the fine-tuned model?
yeah, because
that-
we do
That basically is the last column here is by another factual hallucination detection model. The pre-para is this T5 base, pre-trained on ChatGPT. Fine para is the resulting fine-tuned version. And this is the average result across 3 datasets. So we see slightly less hallucination. Basically, this factual consistency improves.
thanks.
I have another question, sorry. So I was wondering, like, have you looked into controlling the generated paraphrases from GPT 3.5? Because I feel like that will have like a direct effect on the fine tuning performance of the T5 based model.
Do you mean directly using ChatGPT's API?
Or maybe like, yeah, directly using the ChatGPT API. Have you control, I don't know, maybe the
That's
description.
for if you wanna just see the effect on the downstream classification, yes, you can generate paraphrases. But if the ChatGPT makes a error, you cannot fix it. So that's basically the that's basically is one of like these pre-para or here, or even the results here are showing here no tuning. So no tuning means the T5 base from the ChatGPT's output. So we could improve over that by fine tuning.
Okay, good. Let's thank Saeed again.
Thank you.